saw in the last video that the Claisen condensation takes an ester and condenses it with itself to form a beta keto ester, and that the forward reaction is driven forward by a strong equilibrium, a large equilibrium constant, with the deprotonation of the now very acidic hydrogen between the two carbonyl groups. What would it take to do a crossed or mixed Claisen condensation? I believe our textbook refers to this as the mixed Claisen. And this is analogous to the crossed aldol condensation, where we were able to generate one beta hydroxy ketone and therefore one alpha beta unsaturated ketone from a mixture of two different ketones or two different aldehydes. And the key to that was to use one compound that had no alpha hydrogens and therefore could not form the enolate. So if we started with methyl benzoate, it can be a Claisen acceptor, but not a donor. Because of no alpha hydrogen being removed. So it's not possible to make an ester enolate of an ester that has no alpha hydrogens. Methyl benzoate can be the Claisen acceptor. We could then use a different compound. Preferably as the same ester, methyl ester is Claisen, methyl butanoate. That can act as either a Claisen donor or a Claisen acceptor. We're going to use methoxide as our base. Likely ethanol as our solvent. And like the aldol condensation, when we did a crossed aldol condensation, we want to make sure that when we form this enolate, it's not likely to see another methyl butanoate molecule. It's likely to see just methyl benzoate. So we're going to want a solution of methyl benzoate as a base, and then drip this one in slowly. Controlling that order of addition means that this is likely to run into the base and form the enolate, but then it'll be in solution with a large concentration of methyl benzoate and a small concentration of itself, so it's unlikely to do a self-condensation. Exactly the same strategy we used in the crossed aldol condensation. The mechanism is identical to the mechanism of the ordinary Claisen. First form the ester enolate, and the equilibrium that lies strongly to the left. That's just an acid-base reaction. And then that is going to attack the carbonyl group of our methyl benzoate, our acceptor, more or less as soon as it's formed, because of the large concentration of methyl benzoate and negligible concentration of methyl butanoate. There's going to be an excess of this base, so the methyl butanoate dripping into solution has a much better chance of running into a base molecule than it does of running into the ester Steps 2 and step 3 are the nucleophilic acyl substitution, or the acyl addition elimination mechanism. Addition in step 2, and then we'll have elimination in step 3. So no great surprises here. Forming our new CC bond. Mechanism, or the nucleophilic acyl substitution, which is the combination of these two steps. Generating a big keto ester. And then that equilibrium being driven forward by the additional alpha hydrogen. Now has that much lower pKa. Step 4 is to remove that acidic hydrogen, pKa of 11, between the ketone and the ester carbonyl group. And the most prominent resonance structure will be the one with the negative charge on the ketone carbonyl rather than the ester carbonyl. But of course, it's stabilized by contributions from resonance structure with the negative charge on the other oxygen, and of course, resonance structure that puts the positive charge on carbon. And the ability to form these 3 resonance structures instead of just the 2 resonance structures of the initial ester enolate is the reason for the lower pKa of 11 as opposed to the pKa of 25 that we had in our original ester. So the Crossed-Claisen can be done if there's no alpha hydrogen on one of the 2 esters. And any Claisen condensation requires there to be a second hydrogen, right? So it's got to be a primary carbon adjacent to the donor ester. Otherwise, step 4 can't occur, and if step 4 can't occur, you don't really have the driving force for driving the Claisen condensation forward. The product of step 4, of course, is not the beta keto ester. Beta keto ester is the product of step 3, but in a strongly basic reaction like this, there's almost always a mild acid workup. So if you really wanted to be technical about this, we should include step 5, which is protonation of the enolate with mild acid, and that mild acid is often something like 1 molar HCl. So to write the whole reaction out, we start with methyl benzoate, we add sodium methoxide and methanol. Then we add our donor, our methyl butanoate, and then the third step, we use aqueous ammonium chloride to protonate the final intermediate. I won't show the whole mechanism this time, obviously, it's just shown it. But at the end of step 2, what we're left with is this ester enolate and then the ammonium chloride provide that last proton. Give the actual product of the keto ester. Claisen condensation. What's the equilibrium constant for that last step? I written it as the equilibrium. Should I have written it as equilibrium, or is that really a one-way reaction? Well, we know that the pKa is hydrogen sandwiched between the ester carbonyl and the ketone carbonyl is about 11. And we know that the pKa ammonium ion is about 9, so this equilibrium constant would be about 10 squared. That's not an equilibrium that goes to completion, so we rely on the use of excess of ammonium chloride, in large concentrations of ammonium chloride, to force that reaction forward, by which I'm using. What else can we do a Crossed-Claisen condensation? Well, another very common way to effect a Crossed-Claisen condensation is to use a ketone as the donor. And an ester as the acceptor. Even if the ester in this case actually has hydrogens, the alpha hydrogen of the ketone has a significantly lower pKa. 25 here. So if we were to put this mixture into a solution of sodium ethoxide and ethanol, sodium ethoxide would preferentially react with the ketone carbonyl. For the enolate, and I've used the ketone here that has only one type of alpha hydrogen, so we don't have to worry about the base yielding a mixture of two different enolates. This enolate can now react with the ester and notice that I used ethoxide ion because I have the ethyl ester, ethyl butanoate in this case. Step 1, as usual, is proton transfer, form the enolate. And the equilibrium constant for this reaction is less unfavorable than it was for the regular Claisen condensation. It's about 10 to minus 5 now, because the pKa of ethanol and the pKa of the ketone differ by only 5 orders of magnitude rather than 10. Ester carbonyl is attacked. step 2, and then in step 3, you lose the feeding group. And in this case, the product is not a beta-keto ester, but a 1,3-dione. Or a diketone, the last step that drives the equilibrium forward is even more favorable. Because the pKa of the hydrogen between two ketone carbonyls is 2 orders of magnitude lower, pKa of 9, than the pKa of one between an ester and a ketone, or about 11. So now we have resonance stabilized enolate. In this case, there's no particular preference because they're both ketones. We expect to see a relatively equal contribution between the two different resonance structures with negative charges on oxygen, and the equilibrium constant of about because the pKa of the ethanol, around 15, and that is now about 6 orders of magnitude different from the pKa of that hydrogen in between. We would expect that equilibrium constant to be closer to 10 to the 6th instead of 10 to the 4th. That's definitely a one-way reaction, and it's going to stay as this salt, sodium salt, until we add HCl or excess ammonium chloride protein that and regenerate the beta ketone or the 1,3-dione. So it's productive, and we don't have to worry as much about the order of addition because of the 5 orders of magnitude greater acidity. We do have to worry a little bit about the potential aldol condensation. This ketone can undergo an aldol condensation with itself. So we do want to make sure that we have a higher concentration of the ester than of the ketone, or at least that they're in solution together, right? We can't have the ester by itself in the presence of the base, or that equilibrium constant is going to go. But even if the ester reacts with itself, right, that Claisen condensation is reversible, and eventually you're going to drive yourself on to equilibrium is the most stable possible species, which is this mixed Claisen product. So the mixed Claisen condensation or cross-Claisen condensation can productively be done synthetically when one of your esters has no alpha hydrogens and you get your order of addition right, so you're adding your enolizable ester slowly to a mixture of non-enolizable ester and base, or when your donor is a ketone rather than an ester, and your acceptor